Swayam Prabha. Digital India. Educated India.
So, dear students, today let's show you some very special case for the biosensor. So, these things will help you to think about some mechanism, some new concept for the biosensor development. Today's topic is special chemistry for biosensing. So, why I said this topic? As I told you, maybe different background students are here in this class. Let's use your basic fundamental concepts also, because it is not kind of thing that you can remember and then pass the exam, right? You can just use your all the basic background from 10th class onward also you can apply. Let's think kind of chemist, who are the basic chemists. Let's use your fundamental chemistry knowledge for the biosensing applications. Okay, so let's learn this. So today mainly that's why I will cover some basic chemistry today. Then again when I will take some tutorials, that time maybe I will tell you or I will design some questions for you where you can apply not only the chemistry, some your biology concept, your electronic concept, your mechanical concept, that I think you already used your concept for the whole course design. You can see, right? You already have seen. So today just very briefly I want to mention one, your chemistry knowledge. Let's use this. So some special chemistry. Let's show you one very simple reactions. Thing is that platinum nanoparticles, they are highly reactive when the hydrogen can react on the platinum nanoparticle surface very fast. This is electrochemical reactions I am saying. The electrochemical reaction. What is this? Means suppose like your sensor surface, if you have some platinum nanoparticles and if you add the hydrogen into H4 and if you want to oxidize it, electron will be released, right? So then N2 plus H2O will form. This is very basic chemistry, right? Now if only your bare surface like indium tin oxide electrode, if you have only bare surface and if you want to try to oxidize the hydrogen on the bare surface, this oxidation rate, when releasing the electron, this oxidation, right? This oxidation rate will be very slow if there is no platinum nanoparticles. But if there is some platinum nanoparticles, this reaction is very fast. So those electrochemical data I will show you, means how we can determine this is fast reaction or that is slow reactions, how we can determine the kinetics, how we can determine, that I am going to show you now. Let's understand first the theory. This is not just like a theory, this is just your very basic concept that you want to use for biosensing. Okay, so we are very much familiar this one, like hydrogen can react on platinum nanoparticle surface, it is very fast. And this is actually Faraday reactions. What is Faraday reactions? Faraday reactions means this is that we are measuring some like you have the potassium K4 FeCN6, right? And if you measure the cyclic voltammetry, you can remember, right? This is the cyclic voltammogram like this. So in this case, the oxidations and this reduction, this current, the redox behavior, this current is responsible for the Faraday reactions. And non-Faraday's means some reactions that is like chemical reactions that is not involved in this oxidation reduction reactions. Okay, so that is very simplified form. So your Faraday reactions means suppose you are measuring the oxidation current of hydrogen. So you may get the cyclic volt. I will show you the actual cyclic voltammogram just for concept. You may get the cyclic voltammogram of the hydrogen oxidation, something like this. So if you don't have platinum nanoparticle, maybe you may get like cyclic voltammeter like almost zero, very low. You may get very high with the presence of platinum nanoparticle. So you can see based on the current amount, you can say this is very fast reactions. Okay. Now see, if you incubate this platinum nanoparticles and hydrazine with some chemicals called the methylene blue, there will be some reactions. These reactions can affect on this kinetics of like hydrogen reaction on platinum nanoparticle. So hydrogen reaction on platinum nanoparticle, these kinetics can be affected by this methylene blue by another extra chemicals. How? See, hydrogen is reacting very fast, right? This reaction very fast. Now, if you have methylene blue, this methylene blue will reduced in the presence of hydrogen and platinum nanoparticles, and it will form methylene blue reduced form. So, you don't need any kind of potential applications, anything. Your hydrogen actually consuming on the platinum surface because of the methylene blue. Clear? So, methylene blue is kind of a side reactions. It is kind of reactions which is actually consuming the hydrogen on your sensor surface, on your electrode surface. So, methylene blue is consuming the hydrogen. So, it is, that's why it is called side, and it is the competitive reaction. Why it is competitive? Because actual reaction is the hydrogen reacting on the platinum, and we are getting number of the electron, and this number of the electron will be high if the hydrogen concentration is very high. So, it is concentration dependent, right? If it is the high concentration of hydrogen, you will get the higher current. But if your platinum means without any electrochemical reactions, if there is some side chemical reactions, something like methane blue, so it will consume the hydrogen and concentrations of the hydrogen become now low, right? So, that's why it is competitive reactions, and as the hydrogen concentration become low, so your current also become low, you will get lower and lower current. So, more and more methane blue, right? If you have more and more methane blue, more and more hydrogen will be consumed, and more hydrogen consumed means slowly your current of the hydrogen oxidations will be decreased, right? Your hydrogen concentration will be decreased. So, this is the concept of your chemical reaction concept, means your chemistry concept. This concept you can apply for your biosensor development, that I am going to tell you. So, one very basic chemistry you just think. So, how you can apply? So, as I said, if these side reactions actually helping to reduce the hydrogen concentrations. So, if there is no side reactions, then hydrogen will be high concentration, you will get the higher current. And there is a role definitely of the platinum nanoparticles, because if there is no platinum nanoparticle, you can see this C diagram. If there is no platinum nanoparticles, this methane blue will not react with the hydrogen. This hydrogen concentration will not be consumed with time if there is no platinum nanoparticle. So, you should have a platinum nanoparticle. Clear? You can see in the images here, means your methane blue, it is the blue color. At the beginning it is very blue. Now, if the platinum nanoparticle react with the hydrogen, then this oxidized blue form will form the reduced leucomethylene blue, that is the colorless. You can see the F, it become the colorless because of this reaction. But there is, if you keep this reaction for the longer time, this is just for your information, if you keep longer time, your solutions may contain oxygen. So, that oxygen again can oxidize your reduced methane blue, and it may form the again methane blue oxidized form, like you may get again the blue color. Okay. So, this chemistry you should have this information. So, what is the chemistry? Again I am just summarizing that hydrogen can electrochemically oxidize on platinum nanoparticle surface very fast, and you will get the electron that you can measure, like cyclic voltammograph, you can measure chronoamprogram, chronoamprometry, anyway you can measure. Now, if you have methylene blue in the solution, then there will be a side reaction. That side reaction will consume the hydrogen. Hydrogen concentration will be low. You will get lower and lower and lower current. So, your hydrogen concentrations will be depend on the methylene blue concentrations also. If more methylene blue, it means less hydrogen. This concept we will use for biosensor development. Let's use this concept for biosensor development. So, here you can see that one TEM image that we developed some platinum nanoparticle is very small size, like 2 to 3 nanometer size platinum nanoparticle. It is formed by some reduction reaction. What reduction reaction? You may use chloroplatinic acid and add the sodium borohydride, or maybe some other reducing agent. You may get this platinum nanoparticles. Okay. Now, let's use this platinum nanoparticle for biosensor development. So, how we are developing this special chemistry for biosensor development? Let's say this is a sensor surface, and this sensor surface, just like indium tin oxide coated sensor surface, where we immobilize the antibody. Here we use the IgM, means this is the, like you know, the IgG, IgM. So, this is just we use a IgM. This is also a bioreceptor, just a bioreceptor. Okay. So, your bioreceptor ready on the surface, and we will make a solution in a sample tube that may contain few microliters of platinum nanoparticles. Okay, few nanoparticles present and few microliter of hydrogen solution into H4 hydrogen solution, and that solutions will drop on a sensor surface. So, your sensor surface may contain a primary, like a antibody, that can be IgM or IgG, whatever. Suppose we are going to detect a malaria. So, if it is 0 concentration, suppose your sample may not contain any malaria. So, you will not have the secondary antibody, right? There is no malaria antigen, means no antibody. So, we target, let's conjugate your secondary antibody with methylene blue. So, methylene blue can be conjugated with secondary antibody, and methylene blue concentrations we can control based on your target concentration. Say if PF-HRP2 is the target. So, if more target means more methylene blue, because it is secondary antibody already conjugated with methylene blue. So, more target, more methylene blue will get on the surface, definitely. So, as I told you the basic chemistry, that hydrogen concentrations we can tune based on the methylene blue concentration, right. So, we are actually changing the methylene blue concentration based on the target concentration. Now, more methylene blue means more side reactions and hydrogen concentration will be low. At the beginning, if you do not have target, then you will have more hydrogen and you will get very high current. Suppose you are measuring the chronocoulometry. So, at the very beginning, you will have the very high current. Chronocoulometry means you will get the charge, not current, charge, microcoulomb with respect to time. Now, suppose you have some target and your secondary antibody conjugated with methylene blue, and you add all the reagents like hydrogen, platinum nanoparticles, and because of the methylene blue, this side reaction, what will happen? Consume the hydrogen they will consume the hydrogen, and these concentrations will be lower than this hydrogen. So, this concentration will be the higher, right. If there is no target, then hydrogen will be the higher, and if there is target, the hydrogen concentration will be the lower, and low hydrogen then will react on the platinum nanoparticles and you will get the lower current. This is the basic chemistry concept we are using in the biosensor development. Suppose you have the 10 number of targets. So, 10 number of methylene blue will come on the surface and they will consume more hydrogen, and means more hydrogen if they consume. So, actually net hydrogen concentration will be low and your charge slowly decrease, right, like this way. This is just for one example. So, see, this kind of some chemistry knowledge you can try for biosensor development. Let us show you some data. See, these are zero data. See, at the very beginning, if you measure charge versus time, this is coulometry, right? If you measure charge versus time, see, at the very beginning is a very high charge. This is 0, very high charge. Now see, slowly we are increasing the concentrations of the target. So if we increase the concentration of target, it means our methane blue concentration will be increased, and see, slowly this charge decreasing, right? And we can make the calibration curve then, and accordingly we can make, this is the calibration curve, right? So different calibrations that you know, right? Different concentration you can make, and then you can determine the unknown concentrations. I mean, this kind of reactions may not be very much useful for point of care, but you can develop some biosensor. Now, when in this stage, it is not useful for point of care device development, but this is just for a development of biosensor. Now you can think, maybe one project, one idea you may think, let's use this concept for a device development. How easily you can develop this kind of chemistry reaction. Maybe you may have to change some steps, right? You should not involve many step washings or many step handling things on the point of care device, so that end user should not suffer. That you have to improve. But this is just a concept that any kind of this kind of innovative concept you can try for biosensor development. Let's show you another example. This is the second example today I am going to show you. Then I will give this task to you. Let's think some new chemistry concept and let's use for biosensor development. So this is the second example, second and last example for today's class, so that you can think some new concept also. So next class, when I will cover some tutorial, that I will bring some more examples and I will throw the question to you. You may think. See, here the basic chemistry is here in this example. What is this? See, if you have the aminophenol and if you have the silver ion plus aminophenol AP, aminophenol. So you know the aminophenol, it can, so let's show you the basic. I think you just try to remember aminophenol. It can easily convert to what? Quinone, imine, right? This is aminophenol, this is quinoneimine. So if it release one electron, then it will form the quinoneimine, and if you get one electron, then it will form the aminophenol. This is the cyclic reactions I already taught you many times. So these reactions means we can use for biosensor development. See, the aminophenol, it can release one electron. So if you have some electron acceptor, what is the electron acceptor? Silver ion. You can use one silver ion, Ag+. So it can accept one electron from the aminophenol, then it will form silver 0. So silver 0 will be precipitate, right? Silver 0 will be precipitate and aminophenol will form the quinoneimine. This is the very basic chemistry. So aminophenol can form the quinoneimine by releasing one electron. Who can accept this electron? Silver plus. So how will get the silver plus? Let's use silver nitrate salt, Ag plus NO3 minus. So you can make a silver nitrate salt and then add here aminophenol. Then what you will get? You will get silver nanoparticles. You will get, okay, silver 0. Now this silver 0 formation, like similar like before, like more aminophenol means these reactions will be more reactions and more silver nanoparticles will form, and more silver nanoparticles mean now you can oxidize this silver to silver plus again by applying some potential, because it is silver 0 form. No, you can go to again silver plus by applying oxidation potential, right? It is very easy and very interesting. So you made silver 0 on the sensor surface from silver ion. Now let's oxidize the silver 0 to silver ion again. So, if you have more target on your sensor, more target means more target concentrations, then more, see the reactions means more your secondary antibody ALP conjugated. So, you will have more ALP. This ALP, I think I already taught you last few classes, like ALP will react with APP, its substrate. ALP is the enzyme, right? This is enzyme, and APP is the enzyme substrate. So, this enzyme substrate will form aminophenol. So, how will get the aminophenol on your biosensor surface? From this APP substrate. And this, how this APP substrate will form the aminophenol? By reaction with ALP, alkaline phosphate. This is the enzyme. So, more ALP means more APP will react, will form the more AP, and more AP means many silver ion will form the many silver nanoparticles, silver. Now, this is a reactions we can make a cyclic way. I mean, redox cyclic reaction I taught you, chemical, like chemical, electrochemical, chemical redox cycling that I taught you, You can see, if we can anyhow make quinonimine again the aminophenol by using some reducing agent, suppose NADH. NADH is a reducing agent. It will again reduce quinonimine to aminophenol and itself will form NAD plus. It means there will be a redox cycling reaction, right? So, I am just teaching you some to think about some reaction based on your chemistry knowledge. So, what chemistry knowledge you are using here? That aminophenol can convert silver plus to silver 0, and that silver 0 can be oxidized on the surface, you will get the current, and more silver means more current. And you can incorporate here a redox cycling simply by incorporating, by adding on reducing agent, suppose NADH. So, a quinonamine form the again aminophenol and this cyclic reaction will be going on. So, you will get the faster reactions, your signal, you will get the signal amplification. So, if you see the cyclic voltammetry, see in this cyclic voltammetry, see silver plus and aminophenol, this dot line, this one, this cyclic voltammetry you see is actually very high current, this one very high current. Why? Because of these chemical reactions, silver plus and aminophenol, these reactions, and it forms silver 0 plus quinonimine. Because of this reaction, we are getting very high current. Now, if you add here again NADH, reducing agent, again see signal amplified, signal increase. This is called the amplification, right? You are getting the amplifications because of adding the NADH, because of the redox cycling, right? But if see, if you don't have the ALP on the surface, so you should have the AP. If you don't have ALP, means only APP present, no AP. AP means aminophenol. So, only APP, silver plus, NADH will not react. That is why background current C is very low. So, this is your background current, right? Ag plus, APP and NADH is your background current. So, if you background means no target. If you have target, then your APP will form the AP and then this reaction will start. That is right? That I already taught you. So, this basic chemistry I am trying to use in biosensor. See here in this diagram, this is chronocoulometry. You see, when silver plus and aminophenol present, you see that we are getting very high current, this one. Now, if you add silver plus aminophenol NADH, see the current increase, means amplification. This is because what amplification? This is because of the redox cycling amplification, right? Here is a redox cycling reaction. There is a redox cycling reaction. You see, at the very beginning, if you have Ag plus, APP, NADH, there is almost very low current, means this is your background. And you may consider this one as a signal, right? Why we are considering this one signal? Because if you have target, then only this reaction will happen, otherwise this reaction will happen. That is why this is your background and this is your signal. See, there is a signal difference because of the reactions. That is why I am saying this kind of reactions can be used for biosensor development. Something like this way you have to think. If you have some new reaction in your mind, you can try for sensing development also. See, here is the SEM image. See, whatever we are thinking, SEM is kind of the image analysis now you have to do. Like I proposed that because of aminophenol, if you react with silver plus, it will form silver 0. So, let us prove it. How you can prove this? So, this kind of characterization technique also you have to bring in your mind. So, you should give some supporting information that yes, this whatever scheme I am planning, this is actually feasible. See, these cases you are getting small see the particles, you can see they are the silver nanoparticles. In the same way, clearly you can see. It means your reaction is actually working, that is why you can prove this one. Now, in this case, if you add NADH, then I told you this is there is a redox cycling reaction. That is why you are getting the amplification. So, amplifications means more silver nanoparticles should be there. You see, number of not particles and the size also increase. So, this proves that yes, this redox cycling really happened. So, redox cycling reactions, you prove it. So, last slide you prove it by the electrochemically by the chronoamperometric technique, and in this slide I am showing you are proving it by image analysis, SEM image, scanning electron microscopy image, you are proving this one. And in the reactions I propose, we propose that silver plus, if there is a like APP present and NADH present, then there is no silver, right? Silver 0, no. That we are getting the yes, there is no nanoparticle. You see, like here we checked, you check this, you will not see any kind of dots, this silver particle dots. This is also kind of proof that your reaction actually working, and you are using for this target detection. Any kind of target you can detect, that you can apply. Clear? So, this kind of concept let us try. So, you can think. Okay, now let us conclude. First thing, today I just taught, use your chemistry knowledge. Use your chemistry knowledge. So, if you have like a chemical A plus B and is forming C, let us use this one for biosensor development, right. So, in your mind you have one scheme, A plus B forming C. How you will use? So, A, suppose it is a substrate, some substrate, and B you can tag this one with secondary antibody, antibody to secondary antibody you can tag. So, let us manage a biosensor. So, you have the primary antibody. So, let us see, B is in the tag. It means if you have target, then only B come, otherwise B will not be on your sensor surface. So, your A, that is your starting agent, that should react on the surface. So, A, if it form the A ox, means some electron, this reaction should be very slow to get low background, right. To get the lower background, this should be very slow. Now, if A react with the B, A plus B, this reaction should be very fast, then only you will get the signal. So, this control experiment you have to measure before the sensor development. So, you can make a chronocoulometry, let's check. So this is the A and this is the A plus B. This is the A and this is the A plus B forming C. So if you get this much amplification, then only you can use this chemistry for the biosensor development. Although you have in your mind a very good some chemical reactions, but this amplification not that much high, don't use that chemistry, because your signal to background ratio will not be that much high. You cannot detect very low amount of target. Okay, that is a restriction. So let's come back again the scheme. So if you have target here, target, so secondary antibody will bind, secondary antibody already conjugated with B, right. So now A react with the B and forming C, right. Now you will get definitely a very high current, right. So this chemistry, so we are using for sensor development, because so more target means more C will form, you will get the more electron transfer. So accordingly you can make the like calibrations. Slowly the current will increase based on the concentration of the B concentration directly proportional to the target concentration. Clear? This is the topic and very important things I taught you today. And next class again I will teach you some basic very tutorial. I will bring this kind of problem to you and I will show you one by one this problem. Let's think about how this kind of innovations, this kind of independent thinking can be useful for the biosensor development. Okay, thank you. That's all for today.